Hey guys, hope that you're not missing me too much back here in California. I'm actually in my office right now. I'm just going to give you a little bit of video to watch while I'm gone for a few days. Don't forget though, I'm going to be back on the weekend, and we'll be happy to try to help you out with anything you're having trouble with the next homework assignment, or as you're starting to think about studying for the test and so on. So, but I didn't want us to fall behind and get into a real cram at the end of this first section of material. So I'm hoping that you'll be able to make sense of this video that I'm going to produce for you. And the advantage of the video is you can keep rewinding it and watch me say something many times. The downside is you can't really ask me questions that easily. So as you're watching this video, if there are questions, be sure to write them down. Send me an email if you want to get it answered right away. Or if you can wait till I come back, that's also fine. But really, it's no problem. So feel free to keep in touch with me as much as you want. As long as we're going along here, I'll be happy to help you out with it. We had covered sections 2.4 and 2.5 in the book on Monday. And that was all about row reducing a matrix and using that technique to help us solve linear systems. So basically you use the Gaussian elimination process to reduce your matrix to row echelon form by using the elementary row operations. And then once it's in row echelon form, we use this sort of back substitution type of method. Assuming the system has a solution. Back substitution allows us to then solve the system. Okay. So we also talked on Monday about how you can sometimes write the system. It's perfectly fine to write it as a matrix multiplication. So at the time I kind of asked you, well, couldn't we just solve this for x? X being the unknown vector in this equation. And I said, well, you can't divide by a matrix. You just can't do that. And so instead what we did is we built the A-sharp matrix and we went through the Gaussian elimination, as I just explained. Well, it turns out that sometimes it is possible to sort of move the A to the other side of the equation, okay? Which is kind of what you would love to do. You'd love to move the A out of the way so that you have x by itself, right? That's what you would like to solve for. So it is sometimes possible to sort of do that. One thing that we need in order for it to be possible is we need A to be an n by n matrix. So if A is not a square matrix, nothing that I'm going to say today is going to help us. So for the whole day today, assume from now on that A is n by n. It's a square size matrix. If it's not square, we've got to do the Gaussian elimination that I described before. Okay, so here then is a definition. Okay, so given this n by n matrix A, if there exists an n by n matrix B, so the same size, also n by n, such that AB is equal to the identity matrix is equal to BA. Remember the identity matrix? That's the matrix, I'll just put it right here to remind you. That's the matrix where you have ones down the diagonal and zeros everywhere else. It kind of behaves like the number 1. So this is kind of saying that A times B cancel out, so to speak. They become the identity. And so does B times A. Notice I wrote them down both ways around. That's because, remember that matrices don't commute under multiplication. So what AB equals is not always the same as what BA equals. And we're going to require in this definition that A times B and B times A are both equal to the identity. If such a thing happens, so if we have these matrices A and B that sort of cancel out, then we're going to say A is invertible. And and so is B for that matter. It's kind of a symmetric definition anyway. So A is invertible with inverse B. So B is like an inverse for A. Okay, so A and B are inverses in this case. We call B an inverse of A. Okay. However, we do not want to write, so this is just a little warning here. We don't want to divide by a matrix. So don't write something like, B equals 1 over A. Those sorts of things just don't make any sense at all. We want to try to avoid writing anything where it looks like you've divided by a matrix. Okay? We don't want to do that. Here's a question I'd like to address about inverses. We're going to do some examples, of course, in just a second. But let me just quickly address one question that comes up pretty quickly here. Is, can an invertible matrix, so if A is invertible, in other words, if there does exist a B such that AB equals the identity equals BA, can an invertible matrix like that have two inverses? Say B1 and B2. It's a reasonable question. Could we have two inverses for the same matrix A? Let me just call this matrix A right here. So can an invertible matrix A have two inverses? Let's call them B1 and B2. The answer is, ta-da, no. That's not possible. So if there's an inverse for a matrix, for a square matrix A, if there's an inverse, there can only be one. I can explain why. I can give you the reason real quickly. I'm going to suppose that I have these two inverses. I'm going to show they actually have to be the same. Okay? So here's why. Suppose we start with B1. I can write B1 as B1 times I. Remember, multiplying by I is like multiplying by 1. And I can be rewritten as A times B2. Because remember, we're assuming that B2 is an inverse for A. That means, if you believe my definition, that just means when I multiply them together, they become I. Now, we have our rule that we talked about on Monday that says parentheses don't matter when we do matrix multiplication. So I can just reorganize it like this, B1 times A together, and then B2. But what is B1 times A? Remember, we're saying B1 is also an inverse for A, so that's really also just the identity. And then the identity can be dropped because it's just like multiplying by 1. Look what we just came up with there. We started with B1, we did these calculations and ended up saying that it was equal to B2. So the answer is no. You cannot have two inverses for a matrix. You can only have one unique inverse. Because you can only have one unique inverse, we like to write it in a special way. Okay? So we write the inverse, there's only one of them, the inverse of A as A to the minus 1 power. Okay? Again, please don't write 1 over A. When we're dealing with matrices and inverses, we're only going to use exponents here. So we use a -1 exponent for A inverse. Okay. So that's for a square matrix A. If it has an inverse, we have to talk about, we have a lot of things to talk about here. How do we know if it has an inverse? How do we find the inverse, right? Those things we have to still address. But suppose we have an invertible matrix A. Here's its inverse. We're going to write it like that, whatever it happens to be, right? I'm going to show you later how we actually find the inverse. But you can already see why it's going to be helpful to us, right? Because, for example, going back to this system here, if I wanted to move the A to the other side of the equation, I sort of have a way of doing that now. Okay, so if we come back here to this question, if you're trying to take notes on this, which is maybe not a bad idea, if you're taking notes on this, you're going to want to refer back to this question. So maybe I'll put a little star here. You basically take this equation that you're trying to solve, and you just multiply it on the left side by A inverse. Okay? So you have to do it the same on both sides of the equation. So if you're going to put an A inverse on the equation, and you do it on the left side on the left side of the left side, then you also have to do it on the left side of the right side. If that makes any sense. Okay, but what is A inverse times A? Remember, A inverse is the matrix that sort of cancels out the A, right? It just gives you the identity. And the identity can be dropped. It's like a 1, so there you go. Here is the formula for X. This solves our system for us. So isn't that nice? If we know the inverse of the coefficient matrix, assuming that it has one, we simply multiply it by our right-hand side vector b, and that tells us what x is going to be. So, excuse me, that gives us an idea then of one reason why inverses are so important. Okay? Let me talk now a little bit about how we would actually find the inverses of a matrix, okay? If there is such a thing. So maybe some examples here. I think you guys could probably believe me that the zero matrix, for example, the matrix n by n matrix of all zeros, that is not invertible. I mean, you're not going to be able to take a matrix that is all zeros and multiply it by some other matrix such that somehow we get the identity matrix. Because the identity matrix has 1s on the main diagonal, right? You can't take something that's all zeroed out and start doing those matrix multiplication dot products and expect to get anything other than a 0 anywhere in the matrix, right? So there's an example of something that's not invertible. But even matrices that are a little more promising don't always work. I claim that this matrix, 1, 3, 2, 6, it's a 2 by 2 matrix, that is also not invertible. Okay? That may not be so obvious to you. So, I mean, how could you try and find an inverse for this matrix? Suppose that you wanted to do that. You try to find an inverse. You don't know what it is yet, but maybe there's some 2 by 2 matrix that we can multiply that would give us the identity matrix here. And of course we have to multiply in both orders, but let's just even look at just this part of it. Okay? If we try to work this out, look at what happens here. In the upper left corner, so when I multiply this thing out, I'm going to get, let's just do this, a plus 3c, and then over here b plus 3d, right? And down here 2a plus 6c, and then 2b plus 6d. Okay, so that's kind of what we have. And do you see how this is going to be a problem? You see, look, for example, look at the upper right corner. b plus 3d is supposed to equal 0. But if you double it, 2b plus 6d is supposed to equal 1. Well, that's an inconsistent situation if I ever saw one, right? If b plus 3d is equal to 0 and 2b plus 6d is equal to 1, we're going to have a problem trying to solve that system. It's not going to work. So this matrix is also not invertible. Okay? The beauty of the video, of course, is you can go back if I'm erasing too quickly. You can put me on pause or rewind me back and look at it again and make sure that it makes sense to you. Okay? But here's now really where we're heading with this section. This is, by the way, all of this is section 2.6. I should have said that at the beginning. Kind of talking about 2.6 right now. So the question is, how can we decide if A is invertible? And then, of course, if so, how do we find it? And find A inverse. these are the natural questions that you might be asking right now. How do we know if the matrix is invertible, and how do we find it? We see that it has a good use for us. If I have a linear system that I'm trying to solve for x, and the coefficient matrix is invertible, it's going to be great for helping us solve for x, right here. But the question is, how do we know if we even have that inverse? Excuse me. Well, I'm going to answer that question for a 2 by 2 matrix first. Okay. So for a 2 by 2, it turns out it's pretty easy. Okay. Here's what it says. The matrix ABCD is invertible if and only if precisely invertible. Turns out that the secret to this whole thing is AD minus BC. So the main diagonal, A times D, multiply that together, and then subtract the other two numbers, BC. If that is not 0, then the matrix is invertible. So that's easy to calculate, because you just have to do this multiplication, AD minus BC. It's easy to calculate, and even better than that is that if AD minus BC is not 0, we can actually write down the formula for A inverse immediately. Here it is. It's basically 1 over AD minus BC times, so there you see why you need it to be non-zero. AD minus BC has to be non-zero so that I can form this fraction. And then what we do is, and this is one that you're just going to want to remember for the whole semester, it comes up a lot, you swap the positions of the A and the D, and then you put minus signs on the B and the C. Okay? That's it. And you could check that this is right. How do you check if two matrices are inverses of each other? Well, going back to our definition, which I did erase here, but if you go back to the definition again, two matrices are inverses of each other if, when you multiply them together, you get the identity. Okay, so the identity matrix, of course, with 1s on the main diagonal and 0s everywhere else. That's going to happen if I take this matrix times the original matrix A. Okay, that product is going to be the identity. Okay, maybe I'll just show that to you, just so you really believe me. If you don't need this, you can fast forward me this time, okay? So let's say I try to multiply these together. I just want to show this to you. So AD minus BC on the bottom, and we have D and A, and negative B and negative C. That's A inverse, and I'm going to multiply it by the original matrix, ABCD. Okay? If you just do this calculation here, of the product of these two matrices, look what you're getting. AD minus BC. What's the upper right corner? You see I have BD minus BD. And the lower left corner, negative AC plus AC. And then the lower right corner is also AD minus BC. You see? And once I divide by this constant out in front, I'm just going to get the identity matrix. Okay? And it's going to work the other way around also. So you're also going to get, I'm not going to show this part, but if you multiplied them the other way around, you would also get the identity. So that proves it pretty much. Okay. So the main thing I want to get through in the rest of the video here is just, well, how do you answer this main question right in the middle of the board for a larger size matrix? The 2 by 2 case is easy. The 2 by 2 case is very, very easy. Notice, for example, here's a 2 by 2. What's AD minus BC? 6 minus 6 is 0. So this failed to be true, which means the matrix was not invertible. So easy for a 2 by 2 matrix to just test it directly. But that does raise the question, what about a larger size matrix? Okay, so for 3 by 3 or 4 by 4, remember these have to be square size. To determine whether larger matrices are invertible and to find the inverses of them, we have to do a little bit more work. So we need what are called elementary matrices. Elementary matrices. So let me explain what that means. I'll give you a definition here of an elementary matrix. Basically, it's the following. An elementary matrix is obtained by applying one ERO. This is the crucial thing. One ERO to an identity matrix. So this is for any n by n size, whatever the n is. You have an n by n identity matrix. If you start with that and you just do one ERO to it, you get what's called an elementary matrix. Let me just give you a couple of quick examples of that. So here's an example of an elementary matrix. This one is 3 by 3. You see, all that we do to get this matrix is we take the 3 by 3 identity matrix and we permute rows 1 and 2. If I permute rows 1 and 2, I get that. So therefore, this is an elementary matrix. Let's so this one I'll just say this is from P12. Okay. Let's write down another example. Let's suppose we have 1, 7, 0, 1, just a 2 by 2. If I start with the 2 by 2 identity matrix, can you see what the ERO is that would give us this matrix? See what we do the A operation this time. Okay, so remember our elementary row operation notations. So the A operation, I'm going to take 7 times the second row of the identity matrix and add it to the first row. Well, that's just going to put a 7 in the upper right corner there. Okay? So that's also an elementary matrix. Anything that is one ERO application applied to the identity matrix is considered an elementary matrix. Okay. Hopefully so far so good. Here's another example. If I took the matrix 1, 0, 0, 0, 2, 0, 0, 0, 3, is that an elementary matrix? Can I get that from one ERO only? The answer is no, I can't do it. I need 2 elementary matrices to get this matrix, because I have to multiply the middle row by 2 and multiply the third row by 3. So that is not allowed there. Okay? Now the interesting thing is that these elementary matrices basically act like the ERO that they were derived from. So let me explain what I mean by that. If I take this first elementary matrix that I had here, and I multiply it onto some other matrix, let's say A, B, C, D, E, F, G, H, I, if I do this matrix multiplication, I hope you guys are practicing and getting good at matrix multiplication, because we're going to be doing it all semester long, and it's really a fundamental thing. So make sure that you're practicing this. Here's a pretty easy one to practice on. What ends up happening, I'll let you guys check it, but what ends up happening is you actually do end up permuting the first 2 rows of this matrix. We call this A. This is usually we use an E for an elementary matrix. So if I take this elementary matrix, which was obtained by permuting rows 1 and 2, if I apply that to A, I get exactly the matrix that is obtained by permuting rows 1 and 2 of A. And the point is that the elementary matrices basically act like EROs, right? Every time I multiply by an elementary matrix, it's like doing an ERO to whatever the matrix A was.